Hi, momentum and kinetic energy. We have been talking about uh, motions, velocities, and accelerations, and the force is cause motion. And when solving real problems, it is much more convenient or mathematically more viable to define new terms. And the two terms are momentum, also characterize how much motion is there, and also another term is the kinetic energy. All right. So first of all, something is in motion, like this race car. It has a velocity. It goes this way, and we can solve problems with force, Newton's second law, and that all can solve any problem. But in solving problems, and sometimes it's more convenient and more appropriate to define some new quantities. And this is simply a mathematical approach to define these two quantities. One is momentum, which is a vector. So mass times v. So we call it momentum. How much motion is there? You can solve out. And more mass and with velocity, and then multiply together, and you have more momentum. And the momentum is a vector, and it points to wherever the velocity is points to. So momentum is a vector, and it goes in the direction of the velocity. And another quantity, which is also very important, as you'll see later on along the course, and then is called a kinetic energy. And it is defined as mass times v, but this time v squared. If v is a quantity, it's a vector, but you do the absolute value with the speed squared and divide by 2. So half mv squared is kinetic energy. M times v as vector is momentum. Okay, don't confuse the two. Now let's solve some problems. Just get the concept clear. And before we move on, to use this definition to solve some problems. Now the first question is, okay, exercise 4, momentum and kinetic energy. Okay, an 800 kilogram car runs toward the east with the speed 20 meters per second. You can imagine the situation. Just think about it's this car. Okay, 800 kilograms runs toward the east and with the speed of that. So velocity is a vector, but speed is just this much. Okay, A calculates its momentum. Note that momentum is a vector. So how do you do that? So look at the definition. So mass times V. So therefore, momentum, let me switch to the pen. Momentum So momentum, which is a vector, equals mass times the velocity, which is a vector. So in this case, 800 times 20 meters per second, and to the east. So that we call it to the east. So it's 16,000. Okay, and then its units is kilograms meters per second. You just put its dimension there. Momentum doesn't have a name, so simply kilogram meter per second. Simply imply that it's velocity and mass multiplied together. So that's its momentum. Okay, if you write formally, it is this. So it's a vector, so its magnitude 16,000 east. Okay, so then that's momentum. But if the vector is specified with the angle is, whichever with the point, and then you have momentum is vector. So that's A. B is simply apply the concept. So we have this. B, we will have kinetic energy. So we denote this E sub k. In this case, it is a scalar, which is simply a number. Half mass times velocity squared, and half mass, again 800. So again, this is related to same motion, but we just have different quantities. Its kinetic energy is v squared, and it's 20 meters per second squared. If I walk through the mass, I'm going to write it over myself, and it's, so if you figure that out, it is 160,000, although the number is the same, but it's different units. So if you write the units, that units, if you talk about dimension, is kg meter squared and second squared. But in fact, that unit is called joules. You probably heard about this. Joules, and then this is related to later energy, watts and things. So that's a kinetic energy. Energy is in units of joules. How many joules? And later on, you will see 1 joule per second will be 1 watts. You heard about the light bulb that goes by watts, and you have electric energy turn into motion, and then that's how you convert that relate to kinetic energy instead of momentum. But momentum quantity is used to describe how things interact each other spatially, like a collision or fire shots and things. So both are useful, but they all come from Newton's three laws of motion. Hi, we talked about momentum and kinetic energy in previous class. Today we talk about how do we apply these two concepts in solving problems. One thing I would like to introduce is the conservation laws of momentum and kinetic energy. So when an action involves several different objects, they all each have their momentum and kinetic energy. And especially when they are interacting between each other, under certain conditions, the momentum of the total will be a constant. Total momentum may be, for example, if I have one car and interact with another car, and so the total momentum will be car 1 multiplied with the velocity 1, and car 2 multiplied with velocity 2. So this symbol called a sigma is for sum. You basically add up momentum of everyone and as vectors. So you have a total momentum vector. Same idea for the total kinetic energy is half mv squared. You add the kinetic energy together. So these are the situations, and momentum and kinetic energy will be conserved. So look, there are different conditions. For total momentum, which means if the system momentum will stay constant vector if there's no external force exerted on the system. In other words, if there's a collision, the interaction are just between the car themselves, between the several objects themselves, there's no additional from outside of the system. Okay, and of course, depending on what you call a system. Sometimes everything is interacting with each other, but if those external interaction can be ignored, we'll have the momentum approximately conserved. That helps us solve a lot of problems. So total momentum of a system stay a constant vector if there's no external force. Cool? Yeah. Now for the kinetic energy, if several things are if the system stay constant for the kinetic energy, there's no external force, and also, but there's an additional clause for the kinetic energy. If the internal interaction are elastic, which means conservative force, or there's no energy loss of the kinetic energy to other form of energy like heat or electricity or something. If there's no energy loss, and then the kinetic energy will be conserved. Well, most of the time the collision, they are inelastic collision, which means kinetic energy is not conserved, but we will get to energy later on. But so realizing there are different type of conservation conditions. So for momentum is more relaxed. As long as the interaction is between the objects themselves, among themselves, no matter how they each individually changes, and the total momentum stays constant. So let's look at one of the problems here. Okay, say there's two cars collide. So one with velocity to the right, the other one a car to the left. Okay, and in particular we are talking about this exercise. A pickup truck with a mass of 1.8 10 to the 3 kg, that's about 2 tons, and is traveling eastbound and at plus 15 meters per second, which is positive direction. While another smaller car, a compact car, going to the left with 9 times 10 to the second, which means 900 kilograms. Okay, very small, less than 1 ton, traveling westbound and at this negative 15 meters per second. They have the same speed, but in opposite directions. The vehicle collide head-on and become entangled, which is stick together. Okay, that's called totaled. And so now, A, find the speed of the entangled vehicle after the collision. All right. Let's continue solving our problem of momentum conservation on this page. The car collides. So the initial momentum, there are two parts. Momentum from truck and momentum from the car. We call the momentum of the car P1 before the collision. And momentum of the car, we call it P2. So P1 obviously is M1 times V1, and that's 1.8 times 10 to the second and times 15. And P2 is M2 and V2. It's 9 times 10 to the 12 times negative 15 because it's head-on in the opposite direction. Now, so that's P1 plus P2 should be equal to P2, P1 prime. That's whenever I say prime, that means after the collision, P2 prime. So, but P2 prime is they are actually together. So, because of the entangled. So, P1 plus P2, that's the total units together, plus the final velocity of the complex together, which is simply called V prime. So, M2 V2, and so then they add together. So this is to solve, we need to solve for V prime, and then that's what we have. So that's the total momentum before the collision and divided by the total mass. So that we will get. Let's see it on another page. Okay, so yeah, this may be clearer. So that's P1 plus P2, M1 V1 plus M2 V2, and total M, if you would like to call it capital M, that's probably better, and times V prime. So then in this math equation, everything is known except this V prime, the total velocity of the whole complex, the car and the truck. And you divide this to the other side, you can solve for V prime, and then you have this. And then you put all the numbers and realizing that the negative sign in front of the car's momentum and divide by the total mass. You solve this and you will get 5 meter per second. So that's the answer. So they entangled together, they move together with a slower speed. The picture envision, but so one is bigger one hit with another one smaller, and then they combine together with the velocity V of 5. going this way, to the right. All right, part B of the problem. Find the change in the velocity of each vehicle. Whenever you find any change, all you have to do is to subtract between the final velocity and initial velocity. So B, the change, delta V for the truck, for example, 1 is defined none other than V1 final minus V1 initial, and that is, so final is 5, as we see from last slide, minus 15, and that is negative 10 meter per second. So it slows down, becomes 15. Now for the other one, for the car, same idea. V2 change is V2 final minus V1 in V2 initial is V2 final is the same, the 5. However, V2 initial is minus initial is negative, so it's going the other direction. So negative over negative is positive. So it is positive 20. Make sense? Yes. Now, part C, find the kinetic energy change. Why do we want to find the kinetic energy change? We just want to see if the energy is lost into some other form. So let's find the truck. So again, any change, it is before and after. So before, it is kinetic energy for the truck. Okay, K1, it's half M1 V1 squared. And that I just put in a number, half, and let you do the calculation. It's a matter of just pressing the calculator. 10 squared, that's the mass, and the V1 squared, 15 squared. This could be a large number, but you simplify it as 2 to the 10 to the 5th joule. Okay, a lot of energy in terms of joules. So now, after E kinetic energy 1 prime, same, but then 1 M1 V1 prime square, which is 5, and I omitted those calculations. These are part of the same, and then 5 squared, and it becomes this 1.12 times 10 to the 4th. Okay, it's much smaller. It's a order of magnitude smaller, so there's a loss in, so 10 to the 5th and 10 to the 4th. So it's about only 10% of the kinetic energy left. Now let's continue on this new page. We find the change in the kinetic energy. So that's C, the change. So change is always change. Delta change is always the final minus initial. So 1 for the truck change, and the final we find out is a smaller number. It's actually 1.12 times 10 to the 4th joule. So it's smaller. But then before the collision, it was bigger, actually way bigger. 2 times 10 to the 5th joule. So then subtraction, you will get a negative number. It is negative 1.9 times 10 to the 5th. So joule is lost. It's most of the truck's kinetic energy is lost. And if you do the same calculation, so for the truck, so this one for the truck, I will leave this calculation to you, and I will send the calculation as a exercise sheet separately, so to save some video time. So then for the car, and then that is also, so you omitted this, and for the car it is negative 1.04 times 10 to the 5th joule. So the bottom line is that 90% of the kinetic energy is lost in the collision, and it changes to the form of heat, as we will learn in the class later on, is lost. Now, if I add an additional part of the question, part D, well, here's another exercise on definition of momentum. 6p3, this is a problem from textbook. A pitcher claims that he can throw a 0.14 kilogram baseball with as much as momentum as a bullet, which has 3 grams bullet, moving at a speed of 1.5 10 to the third meter per second. That's very fast. It's 1 miles per second. So what must be the baseball's speed if the pitcher's claim is valid? So what it says is that the pitcher's momentum and the baseball, and the same as momentum of the bullet. That's what means as much as it has. So now, if you, and in other words, it is saying that m pitcher times v pitcher. Okay, we don't know what it is, but it has to equal to the momentum of the bullet. So m b and times v b. So what we actually already know is that these two masses we know. So mp is 0.14 kilograms, and mp, the bullet, is much lighter. Bullet is actually 3 grams. Okay, and that is very small. Actually, that's 0.003 kilograms. Very small. So this is known, and we all know the bullet's program speed is very high. So, but the pitcher doesn't have to throw it that fast because his is much heavier. So then the speed of the bullet is known. So 3 of these quantities in this equation is already known. So 1.5, 10 to the third. Okay, it's 10 to the third. So 3 of these are known, so which means mass of the pitcher, mass of the bullet. So then you solve for P. Solve for P of the pitcher. What she has to do? Then this math equation is all you have to do is divide the mass of the divide this by the mass of the pitcher. So divide the momentum of the bullet and then divide this by the mass of the pitcher. So I'm writing with my mouse because I apologize for the equipment I have. All right, so then the speed will be so 0.03. I just ignore the units now because we have all SI units, and 1.5 times 10 to the third. All right, 10 to the third, and then divided by the weight or the mass. Okay, I should not use the weight and mass interchangeably because I'm a physicist. So divide by that. And then, of course, you look at ratio. The small number over big number, that's a fraction. So this number, so if you work through the mass, it will be 31 meter per second. So that's the first one. Now, the second question, part B, which has greater kinetic energy, the ball or the bullets? You would say they have the same momentum. Okay, and so we got this. Circular momentum is conserved, but they may not have the same kinetic energy. So B, so then I use this corner to get this idea. So then kinetic energy is half mv squared. So k ek for the picture. So once again, excuse my writing. So I would say I would just half mv squared, half times 0.5, 0.14, 145, and times 31 squared. So that's its kinetic, is 31 squared. Okay, if I ignore the math steps, so I will get 67. So because it's 31 squared, 67 joules. All right, so 67 joules, that's the kinetic energy. Now, same thing for the bullet, E kinetic energy, also half mv squared bullet. And then that is, okay, half, okay, a very small mass. Well, very small mass, but it's a very high speed. So it's that 1.5 10 to the 6 times 10 to the 6. So you squared, right? Squared and velocity squared. I just drop it. And then that is just, you should do a nicer job. And then that is 3,375 compared to just 65. Okay, it's much higher energy. So because velocity, it is squared. So see, the kinetic energy of the picture is only 67, but that is 3,075. So it's 2 orders of magnitude higher. The bullet has much higher energy. So sometimes kinetic energy, in this case, the bullet has much higher kinetic energy, even though they have the bullet and the ball have the same momentum. Now, same momentum, different kinetic energy. Well, with bullets has much higher kinetic energy because speed is squared instead of linearly proportional to it. Okay, that's the end of this problem. Okay, one last problem on momentum and conservation laws. We will end this chapter. Okay, and a 30 kilogram shell is fired from a cannon, right? It's fired from a cannon of 2,000 kg and with a velocity of 500 meters per second. That's a cannonball, very fast. What's the result velocity of the cannon? So let's think about a situation. Let's say let me draw a cannon like this. So let's say it's horizontally, it'll go like this. So you may have this, and then there's a shell inside, so it's come out of this. Boom. So that's 500 meters per second come out, right? So then the cannonball is 30 kilograms, so 30 kg. Okay, and so then this one is 2,000 kg, much heavier. But in your normal experience, if the cannonball goes forward and then does the cannon itself follows it? No, it's not follows it. It will going backwards, and that is called recoil. If you go so you go that way. So cannonball speed is this way. So, but that's putting in our paradigm. The idea is that this will be solved by momentum conservation. We want to know the resulting velocity of the cannon, which means how fast the cannon just recoil backwards. Boom, this go forward, that go backward. You've probably seen that idea. And this is the same idea, same situation when you shoot a rifle, and the bullets go forward, but the rifle goes backwards. So what is this speed? Okay, and of course we know it's 500 meters per second, goes very fast. So then this is not, so this is again a question of momentum conservation. So before collision, the momentum, and then that is mass of the shell times the velocity of the shell, okay, and which is 0, okay, because before the collision, plus mass of the cannon times the velocity of the cannon is also 0. So that because the velocity, both of them are 0, so before the collision, the momentum of the whole system is 0. Okay, so that's before. After collision, usually we call it prime. So then you will have a shell momentum, so 30. Okay, and then the speed is very fast, 500. And then plus this is 2000, very heavy, and time its new speed, okay, V cannon prime, which means that's what we want to know. We don't know what that is, but with unknown. But we do know that the momentum before, it should be equal to momentum after. If we ignore the friction, we say the interaction are only among themselves. So it's the internal interaction only. So therefore, the momentum is conserved. So if that equal that, then we will have 30 times 500 plus 2000 times V cannon prime, which means after collision. That's a variable we try to find out. Okay, and then that's momentum after. It should be equal to momentum before, which is nothing but 0. So this is P prime. Okay, same as P before. So now, then we solve for this P prime. Solve for P prime, for V prime, V cannon prime afterwards, where it goes. So this once is your math problem. Okay, what do you do? So in this problem, there's everything is known except this. We move this, so V prime C, okay, and that equal to, so we move this to the other side, so negative. If you move any term to the other side, you get a negative, right? 500. Oh, my 5 looks atrocious. Okay, so then divide by 2000. So now it's time to press your calculator, and then you will get a negative 7.5 meters per second. Okay, so it's very slow. Okay, but not only so, it's negative. What does that negative means? Okay, the direction is that if you choose this direction as positive, so that's where the cannonball goes. But then the cannon's speed is negative, so which is this way. So this way is the cannon speed, and that way is the V shell prime. V shell prime go that way, and V cannon prime go this way. So that's 7.5 backwards. So that ends the chapter. If you have questions, we can have a separate discussion. Okay, bye-bye for now.